All right, good morning. Today is Monday. I will be heading back today from my winter vacation, but you will be looking at more examples of this particular concept. Given a polynomial, the degree equals the number of complex zeros. Let's add one more tool to our solving equation belt. That tool is this, the rational root theorem. And here's what it says. A list of possible rational zeros can be obtained by dividing factors of the last term by factors of the leading coefficient. So once again, these are candidates, not actual zeros. Candidates, these are possible zeros for a polynomial. Factors of the last term or constant term divided by factors of the leading coefficient. So here's a good example. Here's a polynomial. What I want to do here is find factors of negative 6. Factors of negative 6. Actually, let's not worry about the negative right now. Factors of 6 are 1, 2, 3, and 6. I will then find factors of 2, which is the leading coefficient, and that's simply 1 and 2. So the theorem says this. The rational root theorem says that I can find possible rational zeros by taking factors of 6 divided by factors of 2. So let's see. Let's take 1, 2, 3, and 6, divide that by the 1, and I get 1, 2, 3, and 6. Then I have to take these four numbers and divide it by the 2. So that means I can take 1 divided by 2, which is 1/2. I can take 2 divided by 2, which is 1, but we already have that. I can take 3 divided by 2, which is 3/2, and 6 divided by 2, which is 3, but that's already on our list. The other important feature is I can have the positive or negative value for these possible factors, possible zeros. So what I've done here is I've listed a possible of 12 numbers that could be zeros to this particular function. Once again, the fundamental theorem of algebra tells us that there's only a maximum amount of 5 zeros. So the list is too big. So once again, these are just candidates that you want to look for to be possible rational zeros for this function. All right. Now, keep in mind too that you don't have to take 5 numbers from this list because you could have imaginary zeros. So let's use that on a couple of examples here. Okay, so what we're going to do with this polynomial is we're going to find all the zeros. All right. Now on Monday we were looking at we can do this graphically with a graphing calculator, but let's use this rational root theorem to help us out. So we're going to find factors of the last number, which is 2. That's 1 and 2. And we're going to find factors of the first, which is 2 as well, so 1 and 2. So we would say that possible, once again, just possible rational zeros are taking the top number divided by the bottom number. So 1 and 2 divided by 1, and then 2 divided by, let's see, I can also do 1 divided by 2, which is the 1/2. And I can do 2 divided by 2, which is the 1. So this is an exhaustive list of all the factors of 2 divided by factors of 2. There are 6 possible candidates. Let's figure out which one works. We're going to start with synthetic division. Okay, so we might start with an easy number. Let's start with just the 1. Let's check and see if 1 is a root. We're going to use synthetic division, and we're going to do this and look for a remainder of 0. All right, bring it down to 2. Let's see, 5, 1, -2. And with the remainder of 0, I now know that 1 is a 0. Okay, this is one of the 4. We're looking for 4 zeros because the degree is 4. And what I have left here is a cubic polynomial, which I can still use the list I provided because my first and last numbers are still 2 and 2. So let's try that again. Let's do another round of synthetic division, and let's see if we can't find another 0. All right, let's try, I don't know, let's try negative. Let's see if -1 is a 0. Bring down the 2, multiply and get 3 when I add. -3 I'm going to add to get -4, and then I get 4 with the remainder of 2. All right, checking my signs here, I see a mistake. Let's fix that. This mistake is right here. This should be a +1. Now, it doesn't change the fact that 1 is still a 0, but it will change the fact that -1 is not. So, doing the arithmetic again, I get 2. Doing the arithmetic again, I get -3. I'll add to get -2, and then multiplying, I get 2, which is the remainder of 0. So I have just found another 0. The other 0 is -1. So there are 2 zeros here, and I'm left with the quadratic. This quadratic is factorable. So let's take that guy and factor 2x squared plus 3x minus 2. Let's use our AC method. It's going to be factors of -4 that add to 3. That's 4, -1. So I can rewrite this as 2x squared plus 4x minus x minus the 2. I can take out a 2x here and take out a -1. And then my factors are x plus 2 and then 2x minus 1. So the other 2 zeros can be found by setting this equal to 0 and solving. So one 0 is -2 and the other is 1/2. So there they are. Let's group these together. From my synthetic division, I got 1 and -1. So 1, -1. And then from the factoring, I got -2 and 1/2. I know I am done because the highest power is 4. Up here, we talk about the highest power being 4 is the number of zeros you're looking for. It turns out that all of these are rational zeros. 1, -1, -2, and 1/2. All of these come from my possible list of candidates, which we found at the beginning, and we're done. One thing we could do is we could make a sketch of this function. It's going to cross the x-axis at 1, -1, -2, and 1/2. The end behavior is such that it's a even positive. So even positive looks like this. So we're going to get a polynomial that goes around and ends up like that. So if you want to, you can graph this in your calculator and verify that what we have is a polynomial that looks like this with the zeros at 1, -1, -2, and 1/2. Let's do that again. Here's another example. Using the rational root theorem, we can say this. We can say factors of the last number, factors of 4 will be 1, 2, and 4. And then we're going to find factors of the first number, factors of 2, which are 1 and 2. So we will find we will find a list of candidates of rational zeros. So we can first divide 1, 2, 4 by the 1 to get 1, 2, and 4. And then we can divide 1, 2, and 4 by the 2 to get more candidates of 1/2. 1 is already there and 2 is already there. So let's see. We also need the positive negative of these 4 numbers. So we have a possible list of 8 candidates, 8 possible rational zeros. So let's start with the 1. Let's see if 1 is a 0. So we're going to put 1 inside the box. And let's see, 2, 15, 31. And to check this, remember, we're looking for, does the remainder equal 0? Let's see, walking through this. Oh boy, that's a bad sign. I'm going to get 48. And I can already see that I'm going to head into trouble here. I don't even have to finish. That is not going to be 0. So I'm going to mark one off my possible list and recognize it is not a rational 0. Let's try another one, negative 1. See if negative 1 is a 0. Let's see. Negative 2, 13. Unless this is 18. Negative 18. Oh, look at, no, it's not going to work out. We get negative 2, not a remainder of 0. So, and that's all right. We're already 2 out of 8, all the way done. So that's 25%. Let's try negative 2. Let's see if negative 2 is a 0. That's the next number on my list. Negative 2. All right, so bring down the 2. We get negative 4, that's 11. Negative 22, negative 9. 18 is 2. And look, negative 2 and 2 make a negative 4. And yes, on my third try, I found a 0. And so I still have to find 2 more to get this down to a quadratic. Let's try, it looks like maybe the negative 1/2 will work. I'm just taking a shot in the dark. But what this looks like is I'm going to take a negative 1/2 here, and I'm going to perform some type division on my remaining polynomial. So I'm going to bring down the 2, multiply and get negative 1. That's going to be 10. Multiply and get negative 5. That's going to be, all right, I did the same mistake before. This should be a positive 9. All right, hopefully change that in your notes. Doesn't change the fact that negative 2 is a 0, but it does help me out here. I get a 4, and then multiply and get negative 2, and there's my remainder of 0. So here we have it. We found from the rational root theorem negative 2 and negative 1/2 to be zeros. What we're going to do now is check for the remaining quadratic to be factorable. An easier way to do this would be to take a 2 out. We get x squared plus your 5x plus your 2. So yeah, factors of negative 2 that add to 5, there are none. Let's use the quadratic formula. So x equals negative 5 plus or minus the square root of 25 minus 4 times 1 times 2. And we'll divide that all by 2 times 1. Reducing this down, we get the exact answer of negative 5 plus or minus the square root of 17, all divided by 2. The 2 approximations will then be negative 4.38. And let's do the other one. I'll take negative 5 minus square root of 17 divided by 2. And that's negative 4.56. So here are the 4 zeros. I found the first 2 by looking at possible candidates, 2 and negative 1/2. So 2 and negative 1/2. And the other 2 are listed here. I'll just put the decimal approximation, and here they are. So with this information, I could make a sketch of this. Let's do that. So the zeros are the x-intercepts. There's 4 of them. There's 1 at 2. There's 1 at negative 1/2. And then there's 1 at negative just to the right of 1/2. And then there's 1 at negative 4.5, about over here. The end behavior is going to get our starting point. The end behavior is even positive. So that means we have the touchdown. It's going to go here and then up here. So let's see. I'm going to go through here. Then I've got to through like that, and then back through. Okay, let's try that again. Boy, this is rough on the third day. My mistake here was the 0. It's not 2. It's at negative 2. So looking at this graph, here we go. So negative 1, negative 2, negative 3, negative 4. Zeros are going to be at negative 4.5 approximately. Negative 2. Negative 1/2, and then just to the right of that. So the end behavior does give me a touchdown, and so what we're going to have here is this. All right, if you graph this on your calculator, this is what you're going to find. And the reason why we want to be careful here is that it looks like on your calculator that we have a multiplicity of 2, meaning a bouncer, but we actually don't. So be careful when you have a function and you graph it. It's not necessarily what it appears because of the graphing calculator.